Please welcome Paul Pilarski.
Presentation. I'm Paul Pilarski. I'm with MnDOT, Minnesota DOT. I'm in the Bridge Construction and Scoping Unit, and my colleague is Mark Chauvin. He's from Janey, Elstner. This presentation is about a long-term review of the treatments to make reinforced concrete last longer. This research was originally in 1997 planned and then executed in the years 1998 and 1999. But at the time we were looking at some new innovative treatments, or new to us, and we wanted to explore how they'd work for our substructures. I was in graduate school at the time. Mark was my colleague. This was actually his graduate project, and so I joined the DOT in 2010. Have been in bridge construction since 2012, and I realized this was out there. We were planning bridge repairs for this project, and it was a unique opportunity to get some research money to look how is it performing 20 years later. So you know you're getting old when you have long-term follow-up of research done during your college days. So what's in it for you as an audience? Today I hope you'll learn about the 3 techniques that we tried to make reinforced concrete last longer. We'll review the initial findings in 1998 and see how they've lasted the test of time. And hopefully you'll take away the number one thing that I feel we have to do as bridge engineers to make our structures last longer or preserve them longer. So in every research project, you need a guinea pig, and our guinea pig or trial location is a bridge just west of Minneapolis. It's actually one of the largest square foot deck areas in our state, so it's a big structure, and it's convenient to access underneath because it's a parking lot or storage area. So it was built in 1967, opened in 1969. There's a forest of piers underneath this bridge. There's over 111 piers. You get lost under there. So really every third pier has an expansion joint, so there's a lot of areas that you could have trouble with degradation. We've replaced the expansion joints in 1977, 1987, and lastly in 2004, but expansion joints can fail the year after you put them in. It just seems like you're whacking moles sometimes. So Mark and I are splitting this and get us good representation here.
Thanks, Paul. As Paul mentioned, this presentation starts by going back in time and looking at what was my research project in graduate school in 1998. And it was a partnership between the University of Minnesota, specifically Dr. Carol Shield, and MnDOT. And at the time, the idea was to evaluate what were new or newer techniques for corrosion mitigation. And so those techniques were implemented on portions of 5 piers of the bridge. Each pier was located below a joint where leakage had been an issue, and there was chloride contamination and corrosion damage. And the techniques which were evaluated were electrochemical chloride extraction, FRP wrap, used not for strengthening, but instead for surface protection or weatherproofing, if you will. And then sealers, which had obviously been established, but were used as a basis of comparison. So I won't go into detail on this, but for those who aren't familiar, electrochemical chloride extraction, or ECE is the easier way to say it, is exactly that. It's a process that uses water and electricity to effectively drive or extract chlorides from an existing element, pulling them out of a structure. So why evaluate it? Well, number one was to evaluate the short-term effectiveness, how much chloride was withdrawn. And then ultimately we went back and looked at the long-term effectiveness. How long did that benefit last? And well, why evaluate it? Well, it's not inexpensive. It's a treatment process, it costs money, and it takes time. That time may be a few weeks, or in our case, a few months. It ran for 8 weeks, or 2 months, on an in-place structure, right? And so in this case, it wasn't intrusive, it wasn't in the way. These were all piers that didn't require any sort of access restrictions for the roadway or anything like that, but for other structures that may not be the case. So if you're going to invest the money, how effective is it, both short-term and long-term? In addition, FRP wrap, again, by that time had been used predominantly for strengthening applications, and this was being used as a form of weather protection, surface protection, trying to prevent moisture and chloride from getting in. The idea being, once you've extracted chlorides, you want to protect the concrete and prevent them from coming back in. However, FRP wraps also have a cost, and in comparison to sealers, that differential is significant. So how much more effective were they? And that was the intent of the research project. And then sealers obviously had been well established, and were certainly cheaper than FRP wrap, but the effectiveness was known to vary. It's obviously highly dependent on the quality of the initial installation, but then even with a great installation, it will tend to degrade in performance with time. So we had these 5 piers, and the treatments were then kind of divvied up to build a matrix where we had elements that we could compare that received similar and different treatments. So 2 piers received ECE, the other 3 piers did not. And then we had different FRP wraps which were used, including carbon fiber, which was applied on ECE treated elements and non-treated elements. We had glass fiber that was similarly applied on ECE treated elements and non-treated elements. We had different sealers, including silane type sealers and more of a special surface finish, kind of a thicker build coating. Those were only applied on the ECE treated elements. And then we had 3 portions of piers which were kept as control. So they didn't receive anything special, just conventional repair, and they were left. No ECE, no surface treatment. And again, they were used to be a basis of comparison to the other elements which had received treatments. So the project started with, again, conventional repairs. Shotcrete repairs were performed in areas of existing corrosion damage. Chloride samples were collected, and that was intended to be a pre-ECE kind of baseline value. And in general, existing chlorides were high at the level of the steel. The ECE process was performed on the 2 piers which were selected to receive it. We couldn't perform it on just a portion of a pier. You had to apply it on the entire pier. And again, for those who aren't familiar with it, the process involves installing a sacrificial anode, kind of a slab mesh, if you will, on the exterior of the element, attached to wood battens that's then encapsulated in a wet cellulose fiber. It's kind of like mushy newspaper. There's electricity that's connected to negatively charge the steel in the concrete, positively charging the anode on the exterior to repel chlorides out of the concrete. Bag it with basically garbage bags, run soaker hoses on it, and keep it wet. And again, in our case, it ran for about 8 months. Following the treatment, chloride samples were taken to compare to the same values we'd taken at adjacent locations before ECE treatment to give us that short-term effectiveness. And we'll touch on it later, but in general, the treatment was very effective. And so chloride levels following ECE treatment in those 2 piers that received it were much lower than they were before treatment. So fast forward 20 years, and as Paul mentioned, this bridge was being programmed for a substructure repair project. And Paul had the foresight to say, hey, we looked at the short-term effectiveness. One of the recommendations was go back and look at it down the road. And that's exactly what Paul decided to do. And so a 2018 study was followed to evaluate the 20-year effectiveness. This bridge has been in service for 20 years after we did all this stuff. How did things shake out? And so the scope of the 2018 study was essentially the same as the 1998 study. There was a damage assessment, damage inspection, which was performed by Collins engineers. So that was visual inspection and sounding to identify locations of corrosion damage. We performed chloride sampling. That was done at as close as we could get to the locations that were sampled in 1998, so we could compare those values after 20 years of service. Half-cell potentials were obtained. You can see the little areas where the FRP wrap was ground down so we could get contact with the concrete surface to generate contour maps and give us a sense of the corrosion conditions within the pier. And then all of that information was mashed together and analyzed just about every possible way we could think to do it. And what we came up with is a bunch of images like this. And this is far too much information for you to digest as quickly as I'm going to fire through this slide. But at a high level, what we tried to do was create one-page summaries to the extent we could that presented all of the information. So on the left-hand side, you've got a couple images of the different faces of the pier cap. Adjacent to that, you've got damage summaries. So you'll see blue shading in areas where delaminations were present in 1998, Red shadings show the locations where delaminations were present 20 years later. You can see there's some areas of overlap. And then on the far right, there's half-cell potential maps, which are taken in 2018. In general, you can see correlation between some of the more negative half-cell potentials and some of the areas of red shading or damage. And then in addition, on the images of the piers, you'll note a bunch of red boxes. And so those boxes were intended to call out where we took core locations. The little number of the identifier is how we identified the core. And then the red shading is an indicator that the chloride level at that core location was above the corrosion threshold at the depth of the steel. Now, the corrosion threshold we selected was 0.035% by weight of concrete, and that was somewhat arbitrary and yet rational at the same time. But a value we used as a basis of comparison. And you'll note there's a lot of red. And there's some red in areas where we don't have damage on that kind of middle image that shows the locations of delaminations. And so that was one of the findings that we wanted to dig into, because in general, the chloride levels after 20 additional years of service were very high. In fact, at the depth of the steel, 86% of all the core locations in the pier caps, the chloride level at the depth of the steel was above threshold, regardless of whether it was FRP wrap, sealer, didn't matter. 68% of all core locations, same thing, chloride levels were high. And in addition, 54% of all the cores we took in the piers which received ECE had chloride levels above the corrosion threshold at the depth of the steel. After we had performed ECE back in 1998, none of the chloride samples were above threshold in the piers. So after 20 years of service, we were kind of right back to where we were, essentially. So why is that? The short answer is we're not entirely sure, but there were some, in particular it was the FRP wrap that was kind of puzzling, because you've wrapped this element, so how did so much chloride get in there? Well, we certainly didn't get a hermetic seal with the FRP wrap. It was installed around, we had to wrap it around the girder seats. A portion of the pier cap on the bottom was left unexposed, because one of the concerns with FRP wrap as a surface protection measure was you've removed the primary tool for a bridge inspector, you can no longer see the concrete surface. So if corrosion continued unchecked behind the FRP wrap, would you know? We didn't know, right? So we left a portion of the pier cap exposed on the bottom, with the idea being if it would allow there'd be a relief valve, so to speak. If a bunch of water was getting in, it could seep out. It wouldn't be trapped, and you wouldn't potentially create this contained corrosion cell. But nonetheless, you didn't have perfect coverage. There's also some instrumentation that was installed, which is the image on the right-hand side, where we were basically coring through the FRP, drilling into the concrete, installing an instrument in a grouted hole. All of these were potential flaws, if you will, in the FRP installation, which could have allowed moisture to get into these elements. In addition, there were differences in the sampling techniques. Back in '98, it was all powder samples. Everything was reported in parts per million. In 2018, we used core samples, sliced core samples, ground up, more accurate, and yet we're trying to compare to kind of these older data values. So, in addition, what we think the biggest variable is that salt usage is significantly greater since 1998. In other words, there's far more chloride exposure between 1998 and 2018 than there was between original bridge construction in 1998. Not only the concentration of chlorides in the different treatment chemicals that are used, but also the number of treatments and pre-treatments and everything else that happens results in substantially more chloride exposure in the last 20 years than there was in the 30 years that preceded that first project. So really, ultimately, that was the only thing that we could point to and feel good about, that was likely the driver of some of these high chloride values. The other side of it, again, was that we saw all these high chloride values, and there wasn't, or chloride levels at the depth of the steel, but there wasn't necessarily delaminations all over the place. So why is that? One of the things we wanted to think about was this corrosion threshold. Again, I said it was somewhat arbitrary. We used 0.035, and that's pulled from various technical literature resources, and ultimately every chloride level just correlates to a risk or a probability of corrosion. 0.035% is maybe a lower risk, 10%, 12%, something like that. Certainly not a guarantee. As the chloride level increases, the probability of corrosion also increases, as shown in the chart. But you can get to some pretty substantial chloride levels, and still, it's not necessarily a guarantee that you have corrosion. But we had this 2019 substructure repair project that was coming up, so we had an opportunity to not just trust a chloride sample, but let's actually take a look at the steel while we're performing repairs and see, is there corrosion or not? And I'll turn it back over to Paul.
Yeah, I'm always a curious guy, so I saw those high chlorides and I was really saying, well, what does that mean for us? We've taken core samples and decks, and sometimes you see extremely high chloride levels and you don't see the DLAM that you think you would expect according to literature. So we knew these cores from 2018 showed high chlorides. We've had mix-ups at the lab, you got to make sure. So we opened a window into some locations, and this first one was within an ECE treated pier, and said, hey, let's go right outside the FRP wrap where it might have had a little more exposure. And that's right near the core that said it had high chlorides. So we opened the window, we had the contractor chipped back to the reinforcing, and we kind of took photos and chloride samples right immediately adjacent to the rebar. And so as you look here, the rebar looks like original construction quality. We didn't find corrosion, and we sent the powder that we chipped off this face right at that excavation level to the lab, and it came back as of 2 samples, it was 0.066%, double the threshold that we were using for corrosion. So we said, well, shoot, maybe that's because it's an ECE treated pier, and it just has this natural tendency to ward off chlorides, repassivate the steel. So we went over to a similar pier that had no ECE. It had the FRP wrap, so you think you'd be getting the benefit there. And we had a core location there that said it had high chlorides again. So we opened the window into this area, and I just wanted to show this, that this was the chloride profiles of that area in 1998 as compared to 2018. So the dashed blue line is the chloride profile. The vertical axis is chloride level, and that's a logarithmic scale. The horizontal axis is the depth into the face of the pier cap. And so going from the dashed blue line to the solid blue line, we were definitely elevated in chlorides over those 20 years, and well above the red threshold line. So we opened this window into that FRP wrap, excavated back to the reinforcing, and you could see the darkened patch there. That was where the old repair was made. And we took a sample, put my little baggie on there, and chipped the concrete in this area that wasn't directly part of the repair mix. And the chlorides came back at 0.2%, so it's nearly 6 times the threshold that we were using. And if you look at the reinforcement there, it still didn't look bad at all. There was hardly any corrosion on it. There was corrosion in the patch area, so it might have been corrosion that they experienced at the time when they were making these repairs. It sandblasted it and they didn't get quite all the chlorides off. But there was no chlorides where we had the 0.2% by weight of sample chloride. So it really surprised me that these elevated chlorides weren't manifesting into DLAM directly. And so we started looking at some other locations. Now this is an ECE treated pier. It's right adjacent to the one we had the 0.2% on. And we did have recurrence of delamination. And this is a ECE treated pier with silane. So looking at this area, there's evidence that that joint was leaking. There's a lot of water exposure. The excavations into the pier to repair this went quite deep. And we did have a high level corrosion activity. That silane was just not able to prevent ingress of new chlorides nor prevent the water absorption to get to the steel. It seems like if you got chlorides in there, it's like kindling, and you add the water, that's the match. So the water is the number one thing that we gotta start addressing and do a better job of. Control it at deck level before it gets to your substructures. We'll turn it back to Mark for the busy slides.
Yeah, so this, again, is more than you'll be able to digest. But when we were trying to tie everything together and evaluate, well, how effective were these different treatments, really, in addition to the graphics I showed earlier, we tried to build some tables, too. And so there's kind of 4 groupings of 3, if you will, combining the treatment. So we had 3 portions of pure caps which received ECE and FRP, 3 which received ECE and a sealer, and then kind of on down the line. And so we tried to group them together, and then the stoplight colored cells, we tried to organize half cell potentials, would be the left-hand pair of columns, and then chloride levels on the right-hand side, and that's chloride levels at the depth of steel. And so at a high level, I think what we'd like you to take away is that we did see some highly negative corrosion potentials that might suggest active corrosion. That would be, I don't have a pointer, but a couple red cells, I guess, on the left-hand side. But it really didn't match the chloride levels that we were seeing, the elevated chloride levels that we were seeing in comparison to that corrosion threshold, which would kind of be that right-hand pair of columns, where basically everything is red. So simply relying on a chloride sample wasn't necessarily the best way to evaluate this, and we really wanted to kind of look at the whole package. But and that would include where distress had recurred, where we had some of these active corrosion potentials, and then if those 2 things, not trusting the chloride without those 2 things, but considering everything all together. And so in terms of damage, we felt that that was probably the best way to truly evaluate things. And so what we plotted here is what we termed a distress ratio. If you take the entire area, surface area of the element, and say it's 1,000 square feet, and then you take the area where there's damage that you need to perform a repair, and you divide the 2, you can get a percentage. So the percent of surface area that's damaged would be your distress ratio. So in 1998, we plotted the distress ratio for the different elements, and that's the orange bar. And the red would be in 2018, and that's grouped by treatment. So what stands out, hopefully, is that for the elements which received ECE and then they were wrapped with FRP, there was no recurrent damage. So 20 years later, we went from a distress ratio that was about 15% or so of the total surface area. 20 years later, there was 0. So the elements which received ECE treatment and FRP wrap performed very well. There was no recurrent damage. Conversely, the next column over is ECE treatment and a sealer, and that is relatively close in terms of a recurrence rate to the columns on the far right, which was the control. So that one received nothing. And the amount of damage that recurred as a percentage or a ratio was almost the same as the ECE treatment with a sealer. The other lower red bar is kind of that 3rd column over, and those are the elements which received FRP wrap, but no ECE. So conventional shotcrete repair, wrap it, and then walk away. 20 years later, the recurrence rate was relatively low in comparison to the control and in comparison to the ECE treated pier, which received just the sealer. Another way to evaluate effectiveness is cost. So in 2018, we had recurrent damage. That damage required shotcrete repairs as a part of the substructure repair. We know what the cost of the shotcrete repairs is on a square footage basis. We know how much we're repairing. So you can evaluate that approximate cost of repair in 2018. We also knew what the cost of treatments were in 1998. And so one way to evaluate it was to essentially add those 2 numbers together, not adjusting for inflation or anything like that, but how much did you spend in 1998? How much did you have to spend in 2018 to repair it? And how does that shake out? And what hopefully you might be able to see is that at the top, for the elements which received ECE and FRP, there was a $0 repair cost in 2018. You didn't have to spend a dime. But the installation cost in 1998 was $91,000 for those 3 elements. Down at the bottom of the chart, you can see the control. The installation cost in 1998 was 0. It was just shotcrete repair. No ECE, no FRP, no sealers, no nothing. 20 years later, yeah, there was some shotcrete repairs that were performed, but the total treatment cost for those elements was $16,000. The other combinations ranged in between. And again, it's not the only way to evaluate effectiveness or evaluate value or what's the right approach, but for this project, it was one way we tried to look at beyond the data, but look at the practical application of what was done. So in summary, the combination of ECE and FRP had very good performance. However, the installation cost is not 0. It's not inexpensive. And for certain special structures, I think it can be a great option, but it may not be a great option for every structure, at least in terms of value, when you consider the ultimate cost, in this case, of the control subset. The combination of ECE and a sealer generally had poor performance, that damage recurred, chloride levels were high, and there wasn't a significant difference or separation between that combination and the controls, which had received nothing. FRP wrap in the presence of leakage is not going to stop chloride ingress. It's not going to prevent damage. And in general, in areas where there wasn't obvious leaking or significant leaking, the FRP wrap alone performed well, performed effectively. But again, if you have leakage, FRP wrap isn't going to save you. Concrete repair without other treatments, so that would be the controls, was generally a cost-effective solution. And in particular, if joints had been maintained, it would have been a very effective solution in terms of dollars invested. But certainly fixing leaking deck joints and investing in regular repair of deck joints is by far the most effective substructure preservation technique. So some additional outcomes, and there's a research report that's available through MnDOT's website. It's probably longer than you'd like, but I would encourage you to take a look if you're interested. Some of these additional outcomes, as I mentioned, we did instrumentation. In general, it was not particularly effective, an effective way to kind of monitor things over time. ECE treatment, again, was very effective. It significantly reduced chloride ions immediately, so the short-term outcome was very positive, that there was a significant reduction in chloride levels. What we learned was that 20 years later, that reduction wasn't necessarily maintained. Lastly, and perhaps most importantly, simply because you have high chloride levels doesn't necessarily mean you have corrosion of reinforcing steel. And the corrosion thresholds that we elected to use, that you may use as a point of reference, may be more conservative than we think. So I'll pass it back to Paul to wrap up.
So what practices are MnDOT using with respect to these technologies? It's easier to maintain and replace fewer joints over time. So like many states, we're trying to minimize our expansion joints, move it off bridge. Even when we rehab a bridge, we're trying to eliminate some joints and shift the movement to a single joint location. In programming bridge preservation, that's a target. When we see CS3 expansion joints, they're moving to the top of the list for which bridges get funding and selected. So we're keeping a high eye on maintaining our joints. Drainage issues remains a problem. If you've got scuppers or troughs on your bridges, we have lots of problems with them. They overflow, they freeze. We get boots and shoes through them, and then it causes pure degradation. So we actually have a research project on detailing better piping systems, because drainage attached to bridges are like the no man's land. Nobody wants to own it. It's like approach panels, and so we just need better detailing guidance for clog-free systems, way oversized pipes, and getting it to off the bridge and away from the columns, not pooling at the bottom of the columns. So galvanic anodes, we are using more of those within the repairs for a time. I mean, I know they recommend putting them in sound concrete where the next generation of deterioration is going to happen. but we've found it to be very expensive, and I just hate chipping out good concrete. So I've rationalized it with pier caps that these delaminations are occurring because of these spot leakages from your joints, and so we're embedding anodes in the repairs at the boundary, or if you've got reinforcement that's still half in, half out of concrete, that's where you're going to get the bang for your buck on the anodes. So we're putting it around the boundary or wherever the steel is still in contact with contaminated concrete. And then with respect to ECE, we know it has a place. It's just not, we haven't used it since 1998. And if we had a historic structure, it probably has legs there. Or you really have to make sure that there's not a lot of steel corrosion in there, make sure it's worth its value, and then you have to have the duration. I know we had 8 weeks for this extraction, and if this pier is in the middle of traffic, that's going to be a problem for that kind of activity. And then the last, for FRP, it is a viable option for strengthening over contaminated concrete. Just got to really make sure you're cutting off the water supply, because it's not going to save you from ingress and new chlorides. You just don't want the delam happening underneath it. I know at some point we were concerned, well, what if that rebar is corroding underneath the wrap? But I think if we can check the chlorides levels, make sure they're not really high, and then cut off the water supply, we have some confidence that the FRP will do its job and not peel off. So I'd like to thank Mark. He spent a ton of time on this project, and the report is very thorough. With Janey kicked in a lot of money to make sure this happened because we were budget limited. And so it just was a really fun opportunity to look back on the project. And the full report is at the link on the screen, and I know we publish these presentations so you can download it at our website. So I'll open up to any questions.
We all know that galvanic anodes work really good to put on top of rebar that's decaying. Have you guys looked at actually using hot tip galvanized rebar for some of your new projects? Because we got case studies of stuff 60 years old where the zinc is still in great shape.
Yeah, we have a 1 Z-bar deck, which is epoxy over galvanizing, and we've got some bridges from the 70s that had galvanizing, and I think they had some issues with the galvanizing back in the 70s, and they moved to the epoxy coated, but we haven't made a movement to the galvanized bar again. I think it has merit there, but it's something that we're going to ease into like everything else.
That rebar, that Z-bar, that was a metallized process, and then the fusion bond epoxy. It wasn't the hot tip galvanized process, but and there is a difference because you got a mechanical bond compared to a metallurgical bond.
20 years, you didn't retreat the silane, did you? Just the original 40% silane for 20 years. It's not going to last that long.
No.
Just so you know.
Yeah, I didn't mean to badmouth it, but it seems like that's our DOT practice. We try something, we walk away, and with our treatments, it's probably that same boat that we put it on once and walk away.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.